welcome to my YouTube channel. In this video we are going to learn how to solve the one-dimensional diffusion equation in Cartesian coordinates. And the diffusion equation in Cartesian coordinates is given as this. Now this equation, this part, the psi here represents the temperature, which is a function of t, and psi here a function of x. So this is the one-dimensional diffusion equation in Cartesian coordinates. So to solve this problem, we assume that this psi represents temperature, right? And it's a function of t and x, and we assume that this psi has a solution of this form: x and t, where x here is a function of x alone, t is a function of t alone. This t is time part, this one is the space part. Now once we are able to determine the value of x, capital letter X and capital letter T, then we substitute them back into this expression, and that's it. So to do that, we need to differentiate this with respect to t once, we keep the answer. We differentiate this with respect to x twice, keep the answer, then substitute them into this original equation. So let's see how it goes. So to differentiate this with respect to t, we have this expression, differentiate this and differentiate this. When you differentiate this, the x part remains constant, so we differentiate this with respect to t. So if we differentiate this with respect to x twice, t will act as a constant, so and that gives us this part. So now we can substitute this. So whenever we see d psi dt in this equation, we substitute this. When we see this one in this equation, we substitute this. So that's what we have now. So from this point on, we can divide both sides by capital letter X, h squared and t to get this expression. So the reason why we did it that way is to be able to get to separate this term and this one's, so that this one will be, the t part will be independent of x and the x part will be independent of t. So that's why we divided both sides. So now that they are separated, this one is equal to this and can also be equal to a constant. So the convenience constant that it will be equal to is assumed to be minus k squared. So we have this one. So that means this one is equal to this and it's equal to this. So we can consider solving this one separately from this one and this one separately with this one. So let's consider this and this. Since this is equal to this, therefore this must be equal to this. So we have this part. So this is the time part. So from the time parts, we can separate this one also using separable variable, taking dt h squared to this side, and let's see what happens. So we have dt all over t h squared, and this small letter dt comes to this side. So we have this. So from here on, we can integrate both sides, and let's see what we get. And this is what we get. If you integrate both sides, you get ln t equal to minus h squared k squared t plus a constant. Now we can make t the separate formula, and in doing so we send this ln to this side, which makes it exponential. So we have t equal to this part. Now we can separate this one using law of indices, and it gives us this part, then e raised power c. Now e raised power c is now a constant. Maybe we can represent it as b or a or whatever, so that will come behind, and that's why we have this one. So t equal to this. So we've solved the time part. So it is now necessary for us to solve the position parts. So we'll come back to this our original equation. At this stage, we can send this equation back, this part here, to this side, so that it becomes dx, d squared x dx squared plus k squared x equal to 0. And this is a typical Helmholtz equation. So to solve this one, we provide this expression, we factorize x out, then our del squared, then k squared equal to 0. And we can see this one can be split into a difference of 2 squared, so that it will bring in the complex number. That's what we have here. So this one and this is given by this one. If you expand this one, it goes back to this. So we can combine this one and x equal to 0, solve separately, then later come back and solve for this x equal to 0. So let's consider this first part, x equal to 0. So we have this part, and from this part we can resimplify this one as dx equal to minus kx. And if you notice, we've solved something like this in the preceding slide. This one will give us dx using separable variable equal to kx. So if you integrate both sides, you have your ln x equal to minus kx plus c. So that's how we have this expression. Make x the Soviet formula. We have x equal to e raised power minus I kx plus c, and that leads us to x equal to these parts, and finally we have a constant here. So instead of solving the other part, we can infer from this first that the other parts, the x2 will be equal to maybe a constant c equal to plus this sign will change, because the difference between this one and the second part is just this sign. So that's why we have x2 equal to b e plus ikx, and from this point our final solution for the position parts will be the combination of these two, and that gives us x equal to this part plus this part. So don't mind we interchange, it doesn't matter, you can play with the constants. So but it's important to write the plus part first and the minus parts. Now at this point, this expression can also be written as this. The proof is not difficult to do. You can expand this one, expand this, and factorize to get this particular part. So sometimes it is more convenient to write your expression, your final solution, in this form instead of this one. So from this point, we can now combine the x and the time parts to give us our final solution. So our psi, which is the temperature, is equal to x t multiplied by t equal to this part and this part. And that's it. Thank you for listening.